Hi everybody. In this video I'll be talking about how to graph quadratic functions in Vertex Form. Before I get into that, however, I would like to simply lay out for you the basic two types of quadratic functions that you will probably see in your Algebra 1A level class and book. The first type is standard form, which looks like this. And standard form is good for many reasons. If you want to use the quadratic formula, if you want to factor and then solve to find out where the x-intercepts are, this is great. It also is good because it could tell you a couple of things. Number one, it can tell you where the y-intercept will be. Okay, now this is the same y-intercept value that you would see in a linear function. In fact, this is the same constant, right? This first term is just an addition to your mx plus b that we saw a while ago. So this still has the same job. The A also tells you about where it's going to be in terms of shrinkage or expansion. If it's going to be wide, it'll be a fraction, something between 0 and 1. Or if it's going to be really skinny, then it would be a number that is bigger than 1. And if it's exactly 1, then it'll be your typical parabola. So I have two pieces of information from here, and I'll go ahead and add this in. So this A value tells you shrinkage slash expansion. It also tells you whether it's going to be right side up or upside down, inverted. Okay? With vertex form, looks completely different, first of all. Look at that, vertex form and standard form. They look very different from each other. But they have some things in common, and there's also some differences. So the letter A still represents shrinkage and expansion. It still represents whether it's going to be right side up or upside down. But we have a letter that standard form does not have, and that's that letter H there. This letter H controls what's called a translation. A translation is simply sliding a graph to the right or left, or moving it up or down. Now, with this particular form, the H represents only right and left movement. Okay, so it's translating to the right or left. The C is a constant, but unlike the standard form, by itself like this, it does not represent the y-intercept. And the reason is, if this were expanded, then this H would have to be combined with the letter C, whatever that value is, to get your final y-intercept. So for that reason, I did not mark this as the y-intercept. And that's the difference between vertex form and standard form. So please keep that straight. All right. It does have another job, though, and we'll see what that job actually is. And I'll go ahead and tell you right now. So the C combined with the H, these two work together to create the location of the vertex. Now, the vertex would be written in standard form. In vertex form, it would be H, comma, C. Okay? So let's go ahead and get into an example and see what this does. So here we go. Example 1. You can see that we have our function right here. We have our space to graph it. We have a table that is, for now, blank. And right away, I have some information that I can share with you. And that is, I know where the vertex will be. The vertex will be at positive 1 and negative 4. This negative 4 pulls that parabola downward to level 4 below the x-axis. Okay, this negative 1, a trick to understanding this is whatever you see here, the location of the vertex will be in the opposite direction of this value. So if it says negative 1, then you go to positive 1. So the location of the vertex will be at positive 1 and negative 4. So here it is, positive 1, negative 4. And because I now know the vertex, I also know where to draw the axis of symmetry. Because it cuts right through the vertex, there it is. And the equation for this line will simply share the x-coordinate of the vertex, which is positive 1. So the equation of my axis of symmetry is x equals 1. And now I need more points because I can't draw a parabola with just a single point. So to do this, I go to my table. And there are other methods to doing this. I will not get into it just yet. but for now we'll utilize this table here. Once you have your axis, choosing input numbers for your table is real simple. I will want to choose a number that's on the left side and on the right side of this line. I could also choose a couple points that are on the left and then just reflect them onto the other side, because for every point I get a second one for free. So I'll go with the number 0, and I'll just go ahead and choose something on the right side of that line. So I'll take a 2, okay? I don't want to choose a 1, because when I choose a 1, I already know I'll get -4. So there's no point of putting that in the table. So this is what happens. You get 0 minus 1 squared minus 4. That becomes -1 squared minus 4. -1 squared is 1. Subtract 4 and you get -3. So -3 is my output, and my order pair is 0, -3, which actually turns out to be our y-intercept. So 0, -3 would be right there. And that's another reason why I said earlier not to simply take the C number and make that your y-intercept when you're in vertex form. As you can see, it's not -4, it's -3. Now, because I have a point here, I get another one automatically for free, and it's just going to be on the other side of this line, the same distance from the line as the original point. So it will be over here. Okay, 2 jumps away, but on the other side. Now, for the number 2, I input that, and I get 2 minus 1 squared. Write that better. Squared minus 4. So that's 1 squared minus 4, which is 1 minus 4. And that is also -3. So what I get is exactly the same thing that I had. Okay, so this is proof that that my assumption about, or my inference about this second point was correct, because the math proves it, right? My point is already there. That's your 2, -3. 2, -3. Now, some people would say, you know what, you should get more points, and I would have to agree with them. So I'm going to go for one more, just because I like to get a nice smooth curve, and I don't like to guess where things are going. So let's choose -1. So this would be -1. Oops, -1 take away 1 squared minus 4, which would be -2 squared minus 4. That would be 4 minus 4, which is 0. So what I just found is an x-intercept. So -1, 0 would be right there. And that's good news for me, because x-intercepts are really important when you're graphing parabolas, whether to know how many you have or if you have any at all. So this is here, which is 1, 2, 3, 4 steps away. And that means that its reflection will be 1, 2, 3, 4 steps away on the other side, or right there. So you can kind of see where this parabola will go through. And actually, I have the finished graph right here. Voila. Okay, here's our vertex, 1, -4. Our y-intercept, its reflection, the x-intercept, the other x-intercept, and the axis of symmetry, which has an equation of x equals 1. And with that, the first example is done. In the second example, I have an a value that is higher than a 1. In the first example, my a value was a 1. So my parabola ended up looking just like a typical standard parabola, see? But in example 2, I almost gave away the answer there. In example 2, my a value is a 2, which means that the parabola this time will be a little skinnier than the first example, okay? I also want to note where the vertex will be. So my vertex, right away, I can go ahead and note this. My vertex will be at, again, go to the opposite of that place. So this will be at +1. And this time I'm moving up 3 times, so it'll be +1 and +3. So +1, +3. There's my vertex. So I mark it with a capital V, since it's an important point, 1, 3. Now I need more points. I can't make a parabola with just this alone, but I know where my axis of symmetry is. It's going to cut through my, oh, that's a horrible job. Let me do that again. It's going to cut right through this vertex, and it is a line, so it does need arrows. The equation of this line is x is equal to positive 1. You just borrow that x coordinate from the vertex. Now, once again, I will choose numbers that are on the right and the left side of this axis of symmetry. So since I'm at 1, I'll choose the number 2. I can also choose the number 0. And it doesn't have to be in numerical order. So if you want to start with 2, go ahead. So this would be 2 times 2 minus 1 squared plus 3. This is 2 times 1 squared plus 3, which is 2 times, actually, let's just jump ahead. So this will be 2 times 1, which is 2, plus 3, which is 5. That's my output and my ordered pair, 2, 5. So 2, 5, where is that? Let's see, 2, 5 is, right here. And I get another one for free, which means that 0, 5 will be my next point. And that means I don't need to actually put the number 0 in there. I can choose a different point, a different number. So I'll go with the number 3 instead. And I expect that this will give me something higher because this is already increasing. So this will be 2 times 3 minus 1 squared plus 3, 2 times 2 squared plus 3, 2 times 4 plus 3. That's going to be 8 plus 3, which is 11. That's my output. And it's not 2. That's going to be 3, 11. And yeah, as I thought, it's going to be way up. So 3, 11, right over there. It's 2 hops away from the axis of symmetry, so its reflection will be 2 hops in the other direction. Or in other words, at negative 1, 11. And as I mentioned earlier, this parabola does look to be a lot skinnier than the first example, and that is, again, because my a value, my a, is greater than 1, and that closes a parabola like a flower in the evening. So here are all my points, and here is the final result. As you can see, it is indeed skinnier than the first one, which is over here. So I hope that these examples helped you out. It's important to gain as much information from the function before you jump into the table, before you jump into the graph, so that you have an idea of what you're supposed to get. And slowing down, I think, is really the key here. Students tend to jump right into things, and they often overlook key material that can give them an important heads up before they actually create the graph. So do slow down, take your time, try to get it right the first time. If you mess up, just go back and fix it. But having a good idea from the get-go is always a good place to start. So I hope this video helped. Please stop by and leave a comment. And again, thanks for watching. Bye-bye.